So first of all, thank you, Lionel, and thank you, Neepa, for organizing this. And also, I mean, it's a nice idea, and it's also very good that we can participate in different time zones and that you have this shifted this to a nice time. It's a nice time. Yeah, and it's my pleasure today to introduce to you Jakub. So Jakub, he studied at Charles University in Prague, and he studied both chemistry and physics, having a bachelor both in chemistry and physics, and then he also got a master in physical chemistry. And during his bachelor and master's, he was working mostly on scattering problems and also on quantum Monte Carlo, so quantum variation in Monte Carlo methods for solving the time-independent Schrödinger equation. But Jakub also, I mean, he loves problem solving, which is also why he very successfully participated in the physics Olympiads and also in the Planck's competitions previously. And he's also now applying all his problem solving capabilities as a PhD student with me at ETH Zürich, where he's working on this exact electron factorization. Now, normally we do this for time-dependent problems, so we are mostly interested in the dynamics of electrons in molecules interacting with strong ultrashort laser fields. But recently we also went back and we looked a little bit more into the time-independent framework, and we tried to work a little bit more on the fundamentals of how this exact electron factorization relates to density functional theory. And this is also what Jakub is going to talk about now. So please, Jakub.
Thank you for your kind introduction, and thank you for the opportunity to speak here. And I'm going to jump right into my presentation. So my presentation, as Axel said, is going to be about exact electron factorization. And more in concrete, I would like to first introduce to you what is the exact electron factorization, what is the relationship to the other density functional theories, and how does the exact electron factorization show electronic structure in molecules. So let's just jump in. So exact electron factorization is going to be thought of as some kind of connection between the fictitious picture of the DFT theories and the full picture of many electron systems described by the Schrödinger equation, or this time-dependent or time-independent version of it. So one side we have theories, Kohn-Sham density functional theories, orbital free DFT, or the time-dependent versions of them. And other side we have the full picture using the Schrödinger equation, and essentially the exact electron factorization is like binds them together. This theory, or like this idea of using this formalism of factorization, it's not new. There already have been some developments in the past. They are mentioned on this left side. But the formalism which I'll be using was later developed in the papers which are mentioned on the right side. So, and to give you a little bit of structure of my presentation, first I'm going to talk what is the exact electron factorization. Then we're going to see how they relate to DFT theories. Then we're going to talk more about, for the concrete model system, about the charge transfer steps. And on the same problem, we're going to look from different point of view from in the geometric picture. So what is this famous exact electron factorization? So if we have, like, for instance, here we have like a sketch of a diatomic molecule. So we have 2 nuclei, the red blobs, and 5 electrons. In chemistry and quantum physics, it is in static picture. It is described by time-independent Schrödinger equation, and that's no news for you. That's standard procedure. But what exact electron factorization does is that this wave function of these n electrons factorizes into 2 parts, into chi part, which depends only on one electron, and the conditional wave function, the phi part, which depends on this one electron. And this factorization can be always done. Essentially, it's the same mathematical thing as in statistics. We have joint probability density, which can be always divided into product of marginal probability density and the conditional probability density. It's just done not with the densities, it's done with the amplitudes. So the wave functions. And to understand more what it means, conditional wave function, what is this phi? This phi is a state of n-1 electrons conditionally dependent on this cyan electron. So it means that this object phi is a state, and if we move the position of this cyan electron, the states of the rest of the electrons changes. So if we move it from the left to the right in this picture, the state of the rest of the electrons changes from this configuration to other configuration in the molecule. And I should also point out, it doesn't, like from the first point of view, it doesn't look like it, but actually this fulfills the antisymmetric condition. So if the whole wave function of all electrons fulfills antisymmetric conditions, then also chi and phi as a product fulfill antisymmetric condition. It's more like hidden inside of them, but they still fulfill this antisymmetric condition. Now, there's one more thing which is interesting about this, and that's this marginal wave function. Except for this marginal, also obeys one electron Schrödinger equation. That's very important because it just, in some sense, it means that we can reduce the many electron problem into just one electron problem. So this one electron Schrödinger equation has 4 terms. Essentially, it has the vector potential. So the vector potential is capturing the relative motion of the other electrons. It's clear external potential. That's very simple. It's just scalar potential of the one electron in the nuclei. Then we have BH, which is the average energy of n-1 electrons, given where is this one other, the nth electron is positioned. And the last term is the geometric potential, which is somehow proportional to how much does phi changes when we change the position of this one electron. And altogether, this follows Schrödinger equation. So I will focus on 2 aspects of this. And the first thing is to emphasize that this way we have exact one electron theory. Exact means that the chi we get from this theory gives us exact, so correct electron density, and in time-dependent version also correct electron current densities. And second thing is that it's one electron theory. So usually, most of the when we are interested in just one electron observables, we don't want to treat with the whole many electron theory. Essentially, if we are interested in one electron observables, we can get them directly, calculate directly from the chi, and so therefore we just have to use one electron theory. Okay, so now after this crash course of exact electron factorization, and when you're experts on it, you're gonna continue on this. And what is the relationship to other DFT to DFT theories? Because somehow they seem similar or like close to each other. And I'm going to talk about the Kohn-Sham DFT, open orbital or orbital free DFT, and exact electron factorization. So the Kohn-Sham DFT, it's clear that this is a system based on fictitious Kohn-Sham system of non-interacting electrons. So it means, so here in this picture, we have a system of 2 electrons, which are in soft Coulomb potential. And they are Kohn-Sham potential, which looks like this. And they occupy these 2 orbitals when they are in semi-spin orbitals state. Then it's clear that the density or electronic density is just sum over all populated orbitals in the system. In the orbital free DFT, it's usually portrayed as some bosonification of the the fermion system. So it's Kohn-Sham system, but now all the electrons are not interacting, but also in the same orbital. So therefore, when it comes to density, so we just have to take the that one orbital and square it, and we get the correct density. And this electron is, in some sense, it's in different potential. So from the Kohn-Sham potential, it differs by this one more term, which is called Paulipotential. That's the picture on the right side when everything is just all the electrons are in this one orbital, and we can see we get a different potential. And the difference between these two potentials is the Paulipotential. And now the third theory, the exact electron factorization, which factors out just one electron in some sense, captures interaction of so it is interacting theory, but all of the n-1 electrons are like average and hidden in some sense, and therefore when we get to the density, we just again have to square the marginal density and we get the correct density. And therefore the picture of the orbital and the potential is the same as in orbital free DFT. But when it comes to potential, it is calculated differently. So it has the external potential and the average potential and the geometric potential. So we know that these potentials, so orbital free DFT and exact electron factorization, they differ up to the concept when you add them all together, but it doesn't tell us anything about if there's any relationship between them individually. We just know as a sum, as together, they has to count as the same potential. So that's all three theories next to each other. And now I'm going to focus on one system which will continue in the rest of the lecture, and that is this diatonic system with two electrons of the same spin. And when we look at the system, so and we look at how the system looks like in the Kohn-Sham DFT picture, and how does it look like in the exact electron factorization picture. So in the Kohn-Sham DFT, each electron is in one Kohn-Sham orbital, and we get this potential, Kohn-Sham potential. And exact electron factorization, everything is just in one orbital, and we get different potential, exact potential. But there is one thing we notice that essentially this corresponds to a situation when molecules is already starting to dissociate. So the nuclei are far enough from each other that the molecules start to dissociate. And when this happens, we observe that there are some step structures in the Kohn-Sham potential, as well as in Pauli, as well as in exact potential. So you can see that there is this bump here, there is some little spike here, and also in other potentials we see them. So this leads me to the next part, and that's what this represents and what is usually called charge transfer steps. So usually this kind of processes, charge transfer processes, are very common in nature, in the world around us. So in general, the picture is we have one molecule or one system, which is usually donor, another which is molecule or system which is acceptor, and electron can transfer from one to other one. That's just charge transfer. It's so common that essentially it's a description of photosynthesis. It happens in photovoltaics when we have reaction in solvents. So it's a very common thing. But the problem is that it's very hard to describe these kind of processes within the DFT theory. So I'll try to explain why. Let's imagine we have here atom 1 and atom 2. They're enough far away from each other so they don't interact very much. So they are relatively separated, but still we have to describe the whole thing as together. And we get these two different Kohn-Sham potentials. Well, we know that Kohn-Sham potential is known up to a constant. So So we get the Kohn-Sham potential of one atom, we get the one other atom. But the question is like how we should how they represent, how they are respect to each other. What is the shift between them? And that's not so quite clear, because depending on that, we get different results. So in the upper picture, we see like they're shifted, like the atom 2 is slightly lower. In the picture 2, they're slightly higher. And as a molecule, as we treat it as a molecule which is dissociating, we see that essentially in the region in between, there has to happen some step. So we get some steps. And these steps are important because if we have this configuration, which is in the upper part, and we start occupying the orbitals, essentially it tells, okay, the one electron goes to one atom and the second electron goes to second atom. That is clear. But if the shift is different, suddenly we get different picture, because then we just put both electrons into left atom, in atom number 1. So depending on this step, we get different results. And this essentially corresponds to charge transfer, because in one situation we had evenly distributed electrons. In other situation, all electrons were on one side. So this is the problem we are dealing with. Now, when we look at the system from the point of view of exact factorization, as I mentioned, there are 3 potentials which we get. So there's the black line that is clear, that's just external potential. And then we get the red line here, which corresponds to average potential. And that's where the bump comes from, the big step comes from. And on top of it, we add the geometric potential, which is mostly a flat line with a little bump here and bigger bump on this side. We add them all together, we get exact potential. Now, the thing is, when you look at the down here is plotted the conditional wave function. So essentially, everything important about the system is hidden in this picture, and I'll try to explain what this picture, what this plot means in this little sketch on the right side. So, if we take this one electron, the x, which is at some position x1, and it's at some positive position, we notice that the second electron is around somewhere at -2, around -2. So it means that the second electron appears at the left atom here. So that's what we see here. But immediately when we move the one electron on to the negative numbers, there happens this swap, this hop, and the second electron suddenly, when we get in this region, hops to other side, to the atom, to the other nuclei. So in this very small region A, this swapping happens. But there's one more swap when we move the one electron all the way on the left side, negative positions. The second electron swaps back to the first nuclei. So we have very clear picture that as we are moving this one electron from one side to other side, the rest of the electrons, in this case, the rest is just one electron, is hopping between the atoms and is somehow reacting to this one electron and corresponds to charge transfer. So it's a very intuitive, mechanistic interpretation of this step and charge transfer. Because as the electron hops from one atom to other one, it has different energy. So that's why we see this step in the potential. To see this more clearly, what is actually happening, I will look into something which is called adiabatic states. Essentially, this is just same idea, very similar idea to Born-Oppenheimer approximation, just with the electrons. So we treat the one electron as nuclei and we move it along, and that way we get these adiabatic surfaces. That's the purple line, and that's the cyan line. And when we look at the potential, we see that it's piecewise, it follows this emetic one-alpha potential. So first, the second electron appears just on one surface, then it hops on the other surface, it follows it, and then again hops back and follows the other adiabatic surface. Okay, so we have some better understanding there, but there's still few things which differ. So actually the exact potential is this dotted line, so which you see here. And you see it differs slightly in this region, and there is also small difference here. And these additional bumps which appear here, they're actually coming from the geometric potential because we didn't treat the geometric potential correct. We didn't add it yet. And this geometric potential somehow is encoding the non-adiabatic effect in some sense of the electrons. So to understand this part, we're gonna jump to geometric picture of our model. So as I said at the beginning, with this conditional wave function, that it's like hops from one side to other side and then back. It's when you look closely to it, it looks like it's essentially it's just one state on one atom and there's second state on second atom, and it just hops between them. So it's very clear suggestion that this can be just very well described using these two states. So essentially, all the second atom is doing is just doing some linear combination between these two states, which can be represented like this. Any state is very easily represented by any point on the Bloch sphere. So it just means that on one pole we have state 0, which is at one atom. Another pole we have state 1, which is on other atom. And what is the second electron doing is essentially traveling on the Bloch sphere from one side to other side. And that's all what's happening. Furthermore, there's one more thing we can tell, that for our system, the whole wave function is the real wave function. So it also means that the conditional wave function is real function. So this gives us some restrictions. So we don't actually use the whole Bloch sphere. We are just using this circle on top of the Bloch sphere, this great circle. And that's only the circle is actually the configuration space where the second electron actually moves around. And okay, so far it's interesting, but there's more. There's more. And that's we get to the geometric potential. The geometric potential means geometric in a sense that it actually corresponds to some scaled distance traveled on this Bloch sphere. So there is very clear connection between how big is this geometric term and how much did we travel on this Bloch sphere, which is expressed in this mathematical formula here, which can be actually reversed. And there is one-to-one correspondence between where we are on the Bloch sphere and what kind of geometric potential the second electron is experiencing there. And we can we have one-to-one correspondence between these two things. Now, the geometric term I said is this green line here. So it means that you see that it's mostly 0. There's something small here, and then there's this bigger bump over here. And when you look at the densities of these two states, so the density so down here we see the logarithmic plot of the density of one state and the second state. We see that the swapping between them happens when the densities change from when one density is dominating over the second density, which makes sense. So we know that this swapping happens at these points. But second thing we also notice is that in this log plot, these lines are relatively like very good lines. They're not just curves, they are very good lines. So very locally, the leading term of how these densities behave and the wave function state itself behave locally very just exponentials. And just using this very simple approximation, we get analytical formula for the geometric part. So this is analytical formula for exactly how this is just essentially just some bump with two parameters, and that's position and how wide is it. And this analytical formula very well describes both bumps. So we see like there's this one very broad bump here. It's almost invisible, but it very well fits this formula. And the second bump, which happens here at around 0. This also tells us that well, we can, as I said, it's there's connection between this geometric potential and the distance. So if we do this kind of integral, we actually calculate the distance traveled, and if we integrate this function we get from the analytical formula, we see that when we get from -infinity to +infinity, we just travel the distance pi, which is exactly what we should expect. That's exactly the distance we travel when we go on the Bloch sphere from one pole to other pole. When we get from one state to other state, that's exactly the distance in radians we travel. So when we compare where we are on the Bloch sphere from the point of view of geometric potential and from the point of view of conditional wave function, we see for these three different distances that they are pretty much on top of each other. Like they're very follow almost the same curve. So there's very good agreement between them. And also we can tell that it's very clear that okay, when the first bump happens, we see we get from 0 to pi. So that's the first transition. We change from one state to other state, and then we move again. And there is second transition, which goes from pi to 2 pi. So it means we swapped again one state for other state. So this altogether agrees very well with this pi change. The second thing is, well, now when we have geometric potential, and from that we know where we are on the Bloch sphere, well, it's just from that easy to calculate like what is the average energy. And we get the second plot here. So the black line is average energy calculated from the exact wave function, and the orange line corresponds to one calculated from the top picture. And they're pretty much on top of each other. And so we see a very good agreement between these two. And in some sense, it tells us that the average energy and the geometric potential, there is relationship between them. There's so if you know one, you can for this case, you can tell something about the other one. Okay, I would like to conclude to the summary of what I presented. So first of all, it's important to tell that exact electron factorization gives us one electron sugar equation. So this is something which is so strong about it that from many electron pictures, it boils it down just to one electron sugar equation. Also, we saw there is close connection between the exact electron factorization and DFT. This is meant in the sense that, okay, exact electron factorization is based on the exact wave function, and the DFT is based on the Kohn-Sham wave function. But these both potentials are instantly the same functionals as the conditional wave function. Then we also showed very intuitive mechanism picture for the charge transfer steps and how the charge transfer happens. And last part is also that the geometric part of potential is also important because essentially it contains all non-adiabatic parts, and it is relevant, it has to be treated. Which also leads to, okay, we didn't solve everything. So I haven't been, so there's one thing I mentioned, the vector potential. but for the one-dimensional systems, it can be removed easily. But open question is what happens for the three-dimensional systems when the vector potential cannot be in general removed, and how relevant is it for such systems? Second thing is what happens if we have more electrons. There was just 2 electron systems, but we're also now working on how this picture manifests itself in the 3 electron systems. And of course, as everyone wants to know, what are some practical approximation, practical methods which can be used, is also what we are working on. But it's better to start the whole thing in the time-dependent picture. Also, at the end, I would like to thank 2 great scientists which collaborated with me on this project, and that's my supervisor Axel Schild from ETH and Axel from Hebrew University of Arizona. And last but not least, this whole thing wouldn't be possible without the funding from Swiss National Science Foundation. So I would also like to thank them. Okay, thank you for your attention, and I'm free to answer your questions.